Hello and welcome to the third lecture of week 10 of the course Introduction to General Relativity. The second lecture was actually split into two parts. Hence, technically, this is the fourth lecture of the week. In the previous lecture, we worked out the Schwarzschild solution, which is the first ever non-trivial exact solution to be written down for the fully nonlinear Einstein field equation. And as I mentioned, it represents the gravitational field of the space-time metric outside a spherical distribution of matter energy. In this lecture, we will study some features of the Schwarzschild solution, and while in the context of Schwarzschild solution, we will uncover an important and fairly generic generalistic effect, namely gravitational time dilation and the associated gravitational Doppler shifting. We will briefly discuss some peculiar features of the Schwarzschild solution, such as the Schwarzschild radius, which turns out to be a coordinate singularity, and the notion of a curvature singularity, which is located at the center of the Schwarzschild geometry. As for references for this lecture, I will cite the following two sources. The first is Carol's lecture notes in general relativity, which is available for free on the archive. This is the archive number. Chapter 4, following pages, will contain the material relevant for gravitational time dilation and gravitational Doppler effect. In Chapter 7, these following pages will contain the material relevant for the discussion of coordinate singularities and curvature singularities in the context of the Schwarzschild geometry. The second reference I will recommend is the textbook by Ohanian and Ruffini. I'm using edition 3, and chapter 4, sections 4.2, following pages contain the relevant material for gravitational time dilation and gravitational Doppler shifting. And chapter 8, section 8.1, contain the material relevant to the discussion on coordinate singularities and curvature singularities. Apart from these, as usual practice, the lecture notes will be posted on the NPTEL-NOC website. Let's look at what's on the agenda today. First, as I said, in the context of the Schwarzschild solution, we will discuss the phenomenon of gravitational time dilation and gravitational Doppler effect. Although we will discuss it in the context of Schwarzschild solution, this phenomenon is actually fairly generic, and it happens in gravitational field in general. It doesn't have to be the Schwarzschild metric necessarily. However, we will discuss this in the context of the Schwarzschild geometry. And then we will discuss the peculiar feature of the Schwarzschild metric, which we had written down in the last lecture, that is the Schwarzschild radius. Okay, this location will turn out to be a coordinate singularity. This is something I will explain what this is, but this is a location where after which the coordinate system cannot be trusted anymore, and we have to replace it. Finally, I will discuss the peculiar feature of the Schwarzschild geometry, which is called the curvature singularity, and it is located at the center of the Schwarzschild geometry, and we will conclude there. Okay, let's first discuss gravitational time dilation. So let's recall the Schwarzschild solution, which is the gravitational field or space-time metric produced by a spherical symmetric mass distribution. In units in which speed of light is 1, the Schwarzschild metric appears like this. Okay. Now, instead of using these big expressions, long expressions, I will use the abbreviation G00, which is minus of 1 minus twice G Newton M over R. For reasons which will become obvious, this is called the redshift factor. And GRR is 1 over this quantity in the denominator. Okay. These metric coefficients, instead of using the explicit form of the coefficients, I'm going to refer by their abbreviations G00 and G sub RR. Alright, so this was just a reminder about how the Schwarzschild metric looks like in units of C equals 1. Of course, if you want to include factors of C, that is, you do not want to use C equals 1, then one need to put an extra factor of C squared here in the denominator. Alright. So, and we also learned about Birkhoff's theorem, which is an important result in general relativity. And this is very fascinating because the matter-energy source, the spherical matter-energy source, can be time-evolving, that is dynamical, while maintaining spherical symmetry and mass. Mass remains the same and spherical symmetry is maintained. For example, one can consider a spherical star which is collapsing to form a black hole, or one can consider an exploding supernova. So this is the star, which, although I've deformed it, but let's assume this is a sphere. In the diagram, it is not obvious that this is a sphere, but let's assume this is a sphere, and if it starts collapsing, maintaining its spherical shape and its mass, then the metric outside will remain, will be given by the Schwarzschild form without any modification. There's no time dependence in the metric, okay? Although the source is time dependent, the metric will not have any time dependence. It is time independent as well as time reversal invariance. These two qualities together define something which is called the static metric, okay? Or it can be exploding supernova. For example, if I have a supernova which is blowing off its outer layers. Sorry about that. Let me just redraw this. And then a further outer layer which has been blown off. So long as the total mass remains the same and the shape remains spherical, an observer far away from the supernova won't be able to tell just from looking at the metric, which will be the same Schwarzschild form. Okay? So the metric is time independent, and in terms of the gravitational radiation language which we learned, the observer far out will not get any gravitational radiation from such sources which are spherical and they're dynamical. So long as the mass is constant, there will be no gravitational radiation. So you might think this is kind of common sense because these are spherical objects, and spherical objects have vanishing quadrupole moments. So gravitational radiation is proportional to the square of the third derivative of the quadrupole moment. So if it's a sphere, there is no quadrupole moment, so there's no quadrupole radiation. But what I'm saying is there's something more stronger, that's further strong, because I'm saying not just quadrupole of any order, there'll be no gravitational radiation, not just of the leading quadrupole order. Quadrupole order, of course, gives you the leading order gravitational radiation. We can have higher orders, octupole, and so on. What I'm saying is that there's no gravitational radiation from such sources, although they're time evolving, so long as they maintain the spherical shape and total mass remains the same, one cannot get any gravitational radiation off them. Now, in the Schwarzschild geometry, consider a fixed location. Okay, so fixed location means fixed value of r, theta, and phi. So d omega. Remember, this is the sphere metric. So this is equal to d theta square plus phi square d phi square. Phi square theta d phi square. Okay, this is the sphere metric, and any point in the Schwarzschild geometry is given by these four coordinates t, r, theta, and phi. Now at a fixed location, one has to fix r, theta, and phi. Okay, so that's why dr equals d theta equals d phi equals 0, because they're fixed. And I'm observing a process happening at this location, so the process has some duration, so dt is non-zero. Okay, the location fixed, but the duration, of course, can be non-zero. Now, for that event, what is the proper time measured by an observer at that location? Let's say it's fixed r. Let's say we take the location to be fixed r. In that case, we know that these two terms on the metric will not contribute because dr, d theta, and d phi is 0. So these two terms don't contribute. Or let's say second line is better. And the proper time, which is given by, remember, proper time is given by minus c squared d tau squared. At this location r, and because their unit c equals 1, so the c square will not be there. And we have this formula that the proper time is given by g00 times dt squared. Okay, remember g00 is a negative quantity because t is the time-like time direction. So g00 is negative, so both sides are actually negative, so this equation is fine. It's not that I'm equating a negative quantity to a positive quantity. The reason is because this time we have a minus 1 here. The factor of g00 on the right side is negative, so it's fine. All right. Now, if you think about it, what is dt? Okay. Now, at a location where g00 is 1, dt is same as the proper time. And the location where g00, which is given by this quantity, is 1, when is r equals infinity. Because at r equal to infinity, this term goes to 0, drops out, and you get g00 to be minus 1. All right. So, since g00 approaches minus 1 as r goes to infinity, we see that the proper time at infinity is equal to the coordinate time, dt squared. So this dt, this coordinate t, is called the Schwarzschild time. So we see that the Schwarzschild time actually corresponds to time measured by clocks at infinity, at spatial infinity, at r equals infinity. Okay, the clocks which are located at spatial infinity, the rate at which they tick, that is the same as the Schwarzschild time. So the Schwarzschild time describes the proper time for clocks at infinity. Okay, so it's important. Anytime we write a coordinate system, it's an important question to ask. Okay, what this time coordinate? Which clock operates with this time? Like which observer's time is this coordinate representing? And for this, the case of Schwarzschild, the Schwarzschild coordinate t, this coordinate represents clocks at infinity. Okay, it represents time in clocks at infinity, spatial infinity. Okay, so we see that minus dt squared is same as minus d tau infinity squared. That is the proper time at infinity. So I can plug it here because dt squared is equal to that, and I get the following equation. So I've taken the square root of both sides, and I've replaced dt by d tau infinity. And we see that the proper time at this location r is related to the proper time at infinity with this factor, square root of minus g00. Since g0 is a negative, I can always write its absolute value of g00 square root. And this tells us that since g00 is generically speaking less than 1, and it is a decreasing function of r, that is, as we go deeper into the gravitational field of the planet or the spherical source, g00 is decreasing. g00 is, of course, magnitude of g00 is maximum at infinity when it is 1. As I come from infinity to inside the gravitational field, 0 decreases. As a result, if g00 decreases, dtr will also decrease as a function of r. So for a given fixed, let's say at infinity, when the clock is 5 minutes, in terms of the clock located at some location r, this will be multiplied by this factor square root of g00, which is less than 1. So what we have is that clocks will tick slower and slower as one moves progressively deeper inside the gravitational field because of this factor g00. So let's say if it is 5 minutes in the clock at infinity, because this factor is less than 1, this might read something like 2 minutes. Okay, because you're multiplying 5 by a factor which is less than 1. So clocks will tick slower and slower. And this kind of phenomena we're seeing in special relativity when moving clocks appear to slow down. So here, what happens is that if you place the clock inside the gravitational field, inside a strong gravitational field, the time will get dilated. That is, it will register less amount of time for an event happening. The clock at infinity will say, in fact, this has been used as input in many science fiction stories, in which if you go deep inside the gravitational potential well of a large star or large planet, in which only few minutes or even few hours pass, but when you come back to Earth, maybe millions of years have passed by. So this effect is real, and it is called the gravitational time-dilation. The fact that if you take clocks inside the gravitational field, the stronger the gravitational field, the slower the clocks tick. So this is the phenomenon of gravitational time-dilation. Although I discussed it in the context of the Schwarzschild geometry, this is a fairly generic phenomenon. The stronger the gravitational field, the slower the clocks tick. And then there is an associated phenomenon which is called the gravitational doppler-effect or the gravitational redshift. So for this, please remember that if I have some clock, for example, it could be an oscillator ticking at the radial location r, the frequency of that oscillation would be given by 1 over nu of r, which is related to this. If d tau is the time period, let me write t and r is the time period, then 1 over nu of r, the frequency of that oscillation, will be given by this relation. And if I plug this on both sides, so 1 over t and r, or 1 over nu r, and this is the frequency of oscillation at infinity, 1 over, sorry about that, 1 over nu infinity. then we get this equation. By inverting both sides, we say that the frequency of oscillation at infinity is equal to the frequency of oscillation at the radial location r times root g00 at r. So this tells you that because g00 again is less than 1, if we have some frequency 5, that frequency will actually, let's consider a situation in the Schwarzschild geometry. So this spherical symmetry, and there is some location which I'm calling E, where I'm emitting light. And let's say that light travels to some location O, where the observer is. So E is for emission and O is for observation. Then the ratio of the observed frequency to the emitted frequency, of course, will be given by this formula, right? Will be given by this formula. So nu O is 1 over this inverse relationship. As you can see, nu O and RO appears here. So for outside, what happens is that as I come outside, G00 will start increasing. So G00 is an increasing function. So 1 over G00 is a decreasing function, and this tells you that the frequency decreases with distance. So if I shoot a light ray of a certain frequency from some location inside the gravitational field outside, as it travels out, its frequency will diminish, and vice versa. If I send some signal of light from outside to inside the gravitational field, its frequency is going to increase, that it's going to get blue shifted. So if the light travels from inside the gravitational well to outside, the frequency gets decreased, that is, if there's a red shifting going on. And if I send something from infinity or outside to inside, then the light will be blue shifted. Okay, so this is a version of the gravitational time dilation, is that we'll have gravitational Doppler effect. Okay, as light moves from a region of less strong gravitational, weak gravitational fields to strong gravitational fields, one could see that there's a blue shifting, and as light moves from a strong region of gravitational field to a weak region, then one must see gravitational red shifting, that the light will get red shifted. Okay, this is the gravitational Doppler effect. So one can obtain the weak field result for this. So for weak fields, we know that G00 can be written in the form of the Newtonian potential, in terms of the Newtonian potential, in this way. And then we can plug in the formula for the gravitational redshift, which is this formula. And what we obtain is that the change in frequency, that is observed minus emitted divided by emitted, is equal to the difference in the potentials. Okay, observed potential at the location where the photon was observed minus the gravitational potential at the point where the light was emitted divided by c squared. So I've brought back c squared because we're discussing a Newtonian result. So this is the Newtonian regime result for gravitational redshifting. And the Newtonian theory, which is different from the GR theory, is that you ascribe the photon with some mass, which is given by h nu, which is the energy of the photon. This you write as mc squared. That gives you the mass of the photon. So if I divide both sides by c squared, I get the mass of the photon. And you think of the photon as a massive particle with mass, which is given by this. And as it moves out of the gravitational potential, well, it loses energy, and hence, because it loses energy, the frequency will diminish. And you can check using this Newtonian logic what is the expression for the frequency shifting, or you obtain, and it will turn out to be exactly the same. So this actually, the general relativistic gravitational Doppler effect formula actually does reproduce the expected Newtonian result, which is no surprise to us. In particular, on Earth, the potential is given by GH. So the change in the potential, of course, will be given by the G times the change in the altitude. So the observed, the altitude of the position where the light is being observed minus the altitude of the position where the light is being emitted from. So that is delta H. So then we have this formula for gravitational Doppler shifting of light in the gravitational field of Earth. Okay, del nu over nu is equal to minus g over c squared times the change in the altitude. So as it goes up, delta H will be positive, and hence the frequency will decrease. As it goes down, delta H is negative, and the minus sign will make it positive. So delta mu will be positive, that is blue shifting. Okay. So if I shoot the light upwards, as the light is traveling up, it will get red shifted, and if I shoot from top to down, then as the light is traveling down, it will get blue shifted. Now this phenomenon was actually observed and verified by Pound and Rebka in 1959. These two are, this was a Harvard physicist, and Rebka was a PhD student, and they first recorded this frequency shift of gamma rays as they descended or ascended some building. In fact, the Jefferson, I forgot the name of the Harvard Physics Department building, but that is where the apparatus was located. And at the top of the building, they would send the light gamma rays downwards, and then they would do in the reverse order, and then they use this Morse-Bohr effect. The Morse-Bohr effect to detect the shift in the frequency of the gamma ray photons, and they found a great match with this formula, which was the verification of gravitational redshifting. And this experiment of Pound and Rebka, which you can read up on the web, is considered to be one of the 4 classic tests of general relativity. In fact, this is the last test to be performed, which is in 1959. So this has been verified and constitutes one of the 4 classic tests of general relativity. Okay. In fact, now we have gone well beyond just verifying it or observing this. We in fact use it in modern day technology, in particular in the GPS. Now remind yourself, the GPS consists of many satellites which are all in motion and at different altitudes. And in order to synchronize their clocks, each one of them has a very accurate atomic clock, which is like accuracy is staggeringly good, like 1/1000th of a second or something like that. But because there are different locations, one has to make corrections for the fact that the different clocks are ticking at different rates in all these satellites. And that synchronization has to be done in sync or in consistency with gravitational time dilation effects, as well as the fact that they're in motion, so there'll be special relativistic time dilation, which you learn that a moving clock ticks slowly. So both special relativistic and general relativistic time dilation effects have been incorporated in the GPS system, and we know it works perfectly. So in some sense, the GPS gives you the first practical application of general relativity, in particular gravitational time dilation or gravitational redshifting. All right, with that we will conclude our discussion of the gravitational Doppler effect. And now we move on to this peculiar phenomenon, which is the Schwarzschild radius, or the coordinate singularity at the Schwarzschild radius. So at the Schwarzschild radius, which is defined by where G00, this G00 factor goes to 0. Remember, G00 is 1 minus twice G Newton times m over c squared. So so at r equals rs, this is 0, which means this is equal to 1. That means you have rs equals twice G Newton m over c squared. Okay, so G00, if you remember from the gravitational redshift formula, tells you that if you have a clock at infinity and it records some time, the time recorded at the clock at location r is related to the time at infinity by a factor of root G00, right? Let me just remind you about the formula. Yes, dtr is root G00 times dt infinity. But what happens at the Schwarzschild radius is this is equal to exactly 0. So the clock freezes. At the Schwarzschild radius, time doesn't pass. It's because there is infinite amount of gravitational redshift. Okay, clocks freeze. Okay, so the clocks will freeze. Also, at the Schwarzschild radius, if you GRR, which is equal to minus 1 over G00, because G00 vanishes at R equals Rs, GRR goes to infinity. Okay, so again, this will lead to infinite amount of gravitational redshift, something which has proper radial proper length dr at infinity. At Rs, it will be stretched infinitely. So this is a very peculiar location. So this cannot be true, right? Because clocks are freezing and lengths are becoming infinite. So in particular, what we will see is that at R equals Rs, the Riemann tensor is finite. Okay, the Ricci vanishes because we know when we constructed the Schwarzschild solution, the Schwarzschild solution respects the Ricci vanishing condition because it's a Ricci flat geometry. So Ricci vanishes, but the Riemann tensor, which measures tidal forces, that is non-vanishing and it is finite. Okay, so there's nothing particularly wrong about this location. Although I'm using the word singularity, nothing really is becoming singular. Nothing is becoming infinity. The Riemann tensor, which represents physical tidal forces, that remains finite, as you can see from the formula. So what is this location about? In fact, it turns out that R equals Rs is a coordinate singularity, where the Schwarzschild coordinate system Tr theta phi collapses or ceases to be a good coordinate system. How do we see that? Well, G00 goes to 0. And if you remember the Schwarzschild metric, it is diagonal. You have G00, and then you have GRR. These are all diagonal entries. And then for theta, theta, and phi, phi, so on and so forth. Okay, so it's a diagonal Schwarzschild coordinate system. Is in the metric looks diagonal in this coordinate system, and G00 goes to 0 at Rs, so the metric degenerates. Okay, and if you remember, one of the postulates of Riemannian geometry was that the metric is a non-degenerate tensor, symmetric tensor. But because we chose this coordinate system, which is called the Schwarzschild coordinate system, we are having to face this unpalatable situation where we have the metric becoming degenerate because one of the eigenvalues is 0 now. Okay, so 0 eigenvalue is the same as degeneracy. So then we say, well, the metric cannot be degenerate, but it's the coordinate system which is at fault here. The coordinate system we cannot trust. Okay, Tr theta phi, we should not trust the Schwarzschild coordinate system for R less than equals Rs. Okay, R greater than equals Rs, it's a okay thing to look at, but the Schwarzschild coordinate system cannot be trusted as we go Rs onward. Okay, so it ceases to be a good coordinate system. Okay, so this is what the definition of a coordinate singularity is. It has a point at which you cannot trust the coordinate system and it doesn't serve your purpose anymore and you have to use a different coordinate system. It does turn out that there exists other coordinate systems, for example, which are called the infalling Finkelstein coordinate system, which does go through Rs without any issues. This location Rs, which is given by this. So this is the definition of coordinate singularity, that a point at which the coordinate system ceases to be a good coordinate system. Okay, and this is, you might think this is something very peculiar and new, but it's actually not new when you learn about the spherical polar coordinate system or the plane. Let's say we look at the plane polar coordinate system when we go from xy to r theta. Then the metric which was given by dx squared plus dy squared. So metric eigenvalues are 1 and 1, non-degenerate. When I write this in r theta coordinate, the same metric appears dr squared plus r squared d theta squared. So this is also diagonal with eigenvalues 1 and r squared. But look at the location r equals 0, which is the origin of the coordinate system. At r equals to 0, this eigenvalue goes to 0, so we have a degenerate metric. So then we say that this plane polar coordinate system is a good coordinate system except for the point r equals 0. So the plane polar coordinate system doesn't cover the point r equals 0. Okay, so this is not only, this is r equals to 0 is also a coordinate singularity, and I'm giving this example of the R2. two-dimensional Euclidean plane and the plane polar coordinate system to show that we actually know about coordinate systems which have coordinate singularities. And the Schwarzschild also turns out to be, Schwarzschild radius also turns out to be a location where the Schwarzschild coordinate system doesn't hold anymore. Okay, RS onwards. R less than equals RS. This is where the Schwarzschild coordinate system doesn't hold anymore, and you have to use an alternative coordinate chart to describe this region. All right, let's plug in some numbers and check what the Schwarzschild radius is for the sun, because it turns out that if we use the Schwarzschild coordinate system, we cannot trust it beyond RS or less than RS. So it's important to get an idea of how big this RS is, and for some standard celestial objects like the sun. So it turns out for the sun, this is incredibly small. It's just 3 kilometers. Okay. Now compare this with the solar diameter or the solar radius, which is 1,000,000 kilometers. So the solar radius is much larger than the Schwarzschild radius. That means, so let me draw the sun. This is the solid object. Which is radius big R, which is 1,000,000 kilometers, and then 3 kilometers is where the Schwarzschild radius is. Okay, somewhere deep inside the sun. So the Schwarzschild radius is located deep inside the sun because the sun solar diameter exists radius exists all the way up to 6 kilometers, and the Schwarzschild radius is just 3 kilometers. So inside the sun we have matter. It's not vacuum. Okay? Far before one can reach the Schwarzschild radius. Okay. Because the Schwarzschild radius is 3 kilometers, but the vacuum solution ceases to apply even before that when R is actually 6 kilometers. So inside one has to of course solve the Einstein field equation with matter, with Kimmy-Newton's non-vacuum solution. So the point is that in vast majority of cases, the Schwarzschild radius is an irrelevant concept. It is immaterial because we will never reach the Schwarzschild solution because matter will start filling up the geometry even before we get down all the way down to the Schwarzschild radius. Okay, this happens for all planets, all stars. It will happen for vast majority of astrophysical objects. The Schwarzschild radius is just a theoretical construct because the Einstein field equations with vacuum Einstein field equation ceases to hold much before we reach the Schwarzschild radius. Okay, that's much larger radius. So the only relevant astrophysical object for which the Schwarzschild radius has some meaning, and it is meaningful to discuss, is black holes. Because black holes, the radius of the black hole will be smaller than the Schwarzschild radius itself. For black holes, of course, the light which is emitted from the Schwarzschild radius will be reflected away to zero. To zero frequency. We know that because it is a point at which G00 goes to 0. So it will have infinite amount of redshift that is completely dark. You will even not be able to see that light coming because it has been reflected. Frequency has been reflected to 0. But actually, it turns out light from 1.5 times the Schwarzschild radius, which is the location of the so-called photon sphere, cannot escape to infinity. So you will not be able to see light signal not just from the Schwarzschild radius, but actually 1.5 times the Schwarzschild radius. Okay, even before that. And we will discuss this in the next week when we discuss light GDZs in the Schwarzschild geometry. Okay. So the bottom line is that for most astrophysical objects like stars and planets, we can ignore the Schwarzschild radius as irrelevant to the discussion because vacuum Einstein field equation will not hold up to the RS. It will be violated even much before that. All right, then let me now discuss the other peculiar feature of the Schwarzschild solution, which is important, which is called the curvature singularity. Again, I'm assuming that the vacuum Einstein field equations hold good all the way up to R equal to 0, which is not very well motivated because for the vast majority of cases we have some matter, and the matter will have some finite radius, so you will not be able to reach R equal to 0 without facing matter. So let's assume that, let's trust that the metric, we trust all the way up to r equal to 0, the Schwarzschild metric. Let me just, this is the Schwarzschild metric, and let's assume this holds all the way from r equal to 0 to r equal to infinity. So in that case, we see that r equal to 0 is truly pathological because the Riemann curvature diverges. And the tidal force will become infinite. So to see this, let's consider something called the Gravitational scalar, which is defined to be the Riemann curvature squared. And as you can see, all the indices are contracted. That makes this called frame invariant. That means its value will be independent of the reference frame. So you don't have to use the coordinate system. I know I said that the Schwarzschild coordinate system cannot be trusted beyond r equals rs, under r equals rs. But let's say if we had some other coordinate system, because this is a curvature invariant, so its value will not change if I do a frame transformation. Okay, and it turns out that this is given by this r squared by r to the 6. As r equal to 0, this diverges to 0. Diverges. Sorry, it should be infinity. Sorry, not 0. So this diverges as we hit r equals 0. So the Riemann curvature diverges and tidal forces are infinite. So this is a truly pathological place, truly bad place, because tidal forces become infinity. And we call such kind of situations where the Riemann curvature or invariance constructed out of the Riemann curvature go to infinity. So again, this is infinity and this is not 0. Curvature singularity. Okay, so one can think of it in two ways. A, spacetime itself ceases to make sense. Just like in a coordinate singularity, coordinates do not make sense anymore. It can so happen that at r equal to 0, spacetime itself doesn't make sense anymore. Or we can say that we obtain the solution from solving the Einstein field equation. Maybe the Einstein field equations do not make sense at r equal to 0. Okay, r equal to 0 is an okay place as a spacetime, but the Einstein field equation, which is leading to this singularity, is not does not make sense at that point. We have to replace Einstein field equation by some other field equation, which will make r equal to 0, the curvature, etc. Fine. Okay, so either of these two possibilities can happen. And the hope is that a quantum theory of gravity will let us know what is the situation. The spacetime itself does not exist there, does not make sense there, or is it that the Einstein field equations do not make sense at r equals 0? So the hope is that a quantum theory of gravity will help us resolve this situation. Okay, with that I will conclude the lecture today, and I'll provide a summary of what we discussed. First, we learned about gravitational time dilation and the associated gravitational Doppler effect in the context of the Schwarzschild geometry, although these are very fairly generic effects happening in any generic gravitational field, but we discussed them in the context of the Schwarzschild geometry. And then we looked at a couple of peculiar features of the Schwarzschild geometry, namely the Schwarzschild radius, which turned out to be a coordinate singularity. That is, the tidal forces are all finite, but the Schwarzschild coordinate system cannot be trusted. Finally, we looked at the r equal to 0, the central singularity of the Schwarzschild geometry. And here we saw that the Riemann curvature, or the invariance constructed out of the Riemann curvature, namely the Gravitational scalar, diverged. That is, the curvature becomes infinite. And as I said, this could represent either failure of the Einstein field equation themselves, which produced the solution, or space-time description, that the fact that space-time can be represented by a metric, that description itself can fail. Okay, space-time might be something else, so which we know for sure, we don't know for sure, and our hope is that quantum gravity will help us settle this issue. Up next, in the next lecture, next week, we will study the Schwarzschild geometry using geodesic probes. Okay, and in particular, we will look at time-lag probes, with time-lag geodesics, which would contain, which would cover orbits of planets and etc. And we will highlight the contrast of this generalistic motion of planets to Newtonian or Keplerian motion. And we will also look at the motion of light in the Schwarzschild geometry, that is, by studying light-like duties in the Schwarzschild geometry. And we will discover a couple more effects. One is the gravitational deflection or bending of light, and the gravitational retardation or slowing down.